Concrete Bridge Modeler is the latest addition to LARSA's parametric modeling software suite. Utilizing LARSA's powerful analytical object modeler technology, AOM in short. This tutorial demonstrates how a complex bridge can be modeled using Concrete Bridge Modeler in just a few minutes. When you start a Concrete Bridge Modeler project, an interactive guide will assist you in quickly creating generic objects. Each step in the guide provides relevant information to help you input the necessary details for defining the bridge objects. We'll begin by importing a section database file created in Section Composer. This file contains the geometric information of the girder section, which features a non-prismatic variation. As observed, after completing this step, the database's guide item changes from yellow to green. The next item is the alignment. This section defines the bridge path coordinate system, which bridge follows. In this example, we define two horizontal control points by specifying a station and a heading for each. After completing the alignment, we proceed to stations. Stations are specific locations where significant changes occur, such as pier locations or section transitions. In this example, we will define the stations for the abutments and pier locations. There will be two abutments at each end of the bridge, with two piers positioned between them. A 30-degree skew angle will be applied to all these points. The first abutment will be located at the origin, and the last abutment will be at station 600. After defining the key locations of the bridge, we can proceed to set up the girders. Before entering the inputs for the girders, we'll adjust the window layout to better visualize the changes in the model. First, we select the section. Next, we assign concrete as the material. And finally, we disable the straight girders option, allowing the girders to follow the curve defined by the bridge path. In this example, we have 7 girders spaced 9 feet apart. The transverse location of the first girder will be set to 0. The transverse locations for all girders will remain the same at both the start and end. Each girder will begin at the first station, located at abutment 1, and extend to the last station at abutment 2. Once we complete the girder definitions, the girder objects will be created. These are AOM's parametric objects defined between the previously entered stations. When the analytical model is displayed, you'll see that the embedded analytical twin has already been generated, with finite elements derived from these objects. After defining the girders, we can proceed to the tendon definitions, starting with the tendon group. The first tendon group will begin at abutment 1 and extend to the pier 1 location. Next, we enter the tendon properties, including the number of strands, strand area, tendon material, jacking force, and loss coefficients. Now we'll proceed with the tendon geometry definition. For this example, we select the reverse parabola option as the tendon profile. First, we define the duct layout, placing 3 ducts along a 20-inch vertical line with equal spacing. Next, we will define the positions of the duct layout along the tendon profile. At the start, the duct layout will be positioned 15 inches below the top flange of the girder. At the midpoint, it will be 60 inches below the top flange. And at the end, similar to the beginning, it will return to 15 inches below the top flange. As seen in the model, tendon groups extending between abutment 1 and pier 1 are created for all 7 girders. We will follow the same procedure to create tendon group 2, which extends between pier 1 and pier 2, and tendon group 3, which extends between pier 2 and abutment 2. However, this time we don't need to re-enter the tendon properties or geometry. We will use the same properties in tendon profile defined for tendon group 1. After updating the model, all tendons are created for each girder, and the discretized tendon elements, aligned with the line elements, are stored in the embedded analytical twin. Next, we move on to the deck definition. We set the deck thickness to 8.2 inches, with 4.5 feet overhangs on both sides. Concrete with a 4 KSI compressive strength is used as the deck material, and medium mesh refinement is selected. The deck object and shell elements in the embedded analytical twin have been created, with the connectivity between the shell and line elements automatically managed. The final item in this tutorial is the substructure definition. In this example, pin supports will be assigned to all supports. However, this section also allows for the definition of piers, with or without cap beams. With the completion of the final item, the model is fully constructed. The embedded analytical twin comprises a total of 22,473 nodes, 1,377 line elements, and 22,011 shell elements. Now we can export the model to LARSA 4D via the File menu. All the finite elements stored in the embedded analytical twin are exported as a LARSA 4D model. When the exported model is opened, all elements from the embedded analytical twin are transferred to the LARSA 4D model. This concludes our concrete bridge modeler tutorial. We hope you found this video helpful, and we invite you to contact us for more information. Stay tuned for future updates.